Hello, water managers and SWMS users. I'm Russell Errett. I'm from the Water Management Systems Division out of the Hydrologic Engineering Center. My presentation today is going to be on SWMS implementation, and we're going to be using St. Louis District as an example. This is the second part of a multi-part series. So we just went through the St. Louis District overview and got you familiar with the St. Louis District in the previous part, and then also how precipitation has been viewed before we do any SWMS modeling. So now for this part, we're going to go through and start digging into how SWMS has been implemented in the St. Louis District, and give you an example of how that has been implemented and put into workflow for the St. Louis District water managers. And then in subsequent parts after this, we're going to go through the applications of SWMS and how it's been utilized within the St. Louis District and give you some real-world examples of SWMS usage within the district, and then show you how we've used that to compare the new SWMS paradigm with the legacy process. So after we view precipitation and kind of have an assessment of what's going on with the watershed, we're able to kind of give ourselves an idea which direction we need to go to. We start to get into the modeling part of it, or the SWMS-CWMS part, if you will. And so the first thing we do before we actually do any physical modeling is we start to do more viewing of data. So we're going to view the actual time series data and start editing and validating data. So this is kind of where some of the daily workhorse operations happen. So this is where we first start opening the SWMS-CWMS. And so this is an example of the Salt River watershed in northeastern Missouri. And so this is the CWMS we open up, and the first thing we will see that we start with is the visualization tab. So the first thing you'll probably notice is that the time series icons within this watershed are not geographically oriented. They're not spatially referenced within the watershed itself. They're kind of pulled out in a grid format. So you can see the red dots indicating where the stream gauges and precipitation gauges are in and around the watershed. But these time series icons are not within that watershed. And there's a reason for that. One is for the ease of access to get to those gauges. If they're spatially referenced, sometimes they're on top of each other. There's a pool and tailwater gauge right on top of each other. They're hard to get to. Also, as we will show later on, the modeling schematic goes inside of this watershed. So it becomes very cluttered to try to go through modeling components and also time series components. So I try to split those out so that they're separate and easy to access. One thing you might think is that it's hard to figure out where these gauges are located. As a water manager that used to work in St. Louis District, anyone that operates watersheds or reservoirs or projects within the St. Louis District and water management needs to know where these gauges are at. And if they don't know where they're at, they need to do more research or open a water control manual and get more familiar with the watershed before they actually get into the operations component of it. So there's kind of a learning curve to that. And so once they know that, they'll know where all these gauges are at. And that needs to be known before you actually really dig into and do deep dives into operations. So there is some logic to the madness that occurs with these time series icons. The upper time series icon is the most upstream gauge in the watershed. And as we go down this list, it's working its way down the watershed closer to the reservoir. So these are actually tributaries that are coming into the reservoir. And then we get to kind of the reservoir overview time series icon. And then over here to the right, we have the reservoir, and then we have the downstream gauges as we work our way downstream all the way to the Mississippi River. So it's kind of in a hydrologic order. And all of the watersheds within St. Louis are set up in a very similar fashion. They're probably configured a little differently just based on the shape of the watershed and how they fit in the CWMS window. But they're all very much designed the same way with the grid format for each of the projects. So a couple of things to also notice over here on the left, there's a couple different ways to set your time windows. There's a kind of an explicit time window if you're looking at a very explicit time if you're trying to evaluate things. Generally for operations, we're always looking at it into a relative sense. So we're looking back, for this example, 7 days back and looking 0 days forward. So we're looking at the observed record. And so a couple things to look at. We start to look at just an upstream overview. So I have a time series icon that's been created that kind of gives us an overview. So it has the reservoir elevation, and then it has the inflows coming into that reservoir. And so to give you a frame of reference to this reservoir, the guide curve at Mark Twain Lake is 606. So this is the bottom of the flood control pool. And then you can start to see here on the 2nd of August, we start to encroach upon the flood control pool. And so to give you an idea of where the top of the flood control pool is, 638 is the top of the flood control pool. So this is not anywhere near the top of the flood control pool, but you can see that we're getting encroaching upon the flood control pool. We're probably getting close to roughly 25% full-ish in that range here with this flood event. which is kind of abnormal. This is August. It's typically the dry period within the Midwest, so these events are relatively rare. So we're typically in a drier pattern for this. So this is kind of one of those abnormal events that happen. Things that to look at, there's a lot of stuff going on here. There's a lot of tributary gauges. This is one of the newer projects within St. Louis. So there's a luxury of gauges within that network just because it's newer and it happened to have a lot of stream gauges before it was designed and built. And so that's a great part for this watershed. It's fairly easy to forecast for inflow forecast because there's a good gauge network. And so the things to think about is looks like 2 different events. Also, there's a lot of gauges going on here. So now we're going to have to start digging into each individual gauges. And then so also going downstream, we have a downstream overview, but we can start pulling up the tributary gauges that are downstream. There's actually only one stream that is gauged downstream. This is Spencer Creek. So you can see the first event that's on the 2nd, 3rd, and 4th doesn't really affect the downstream area. There's not any inflow coming into the downstream area. So this would indicate that the majority of the rainfall happened upstream of the reservoir, which is good for the downstream landowners that are primarily agricultural. So that's going to protect them downstream. And you can see the secondary event starts to be a little bit more over the whole watershed. Channel capacity on the lower Salt River is close to 12,000 CFS. So you can see we're not getting anywhere close to that with this tributary gauge. So this is actually a really good event to kind of think about flood damage is reduced, keeping flows within banks and protecting agricultural damages downstream. And so if we start digging in through some of these gauges, we can also look at the precipitation with it. Does the precipitation correlate to what we're seeing on those stream gauges? So we can also put the gridded precipitation in here. So we talked about how we looked at it in MET view before we get into the model. We can look at it again from the CAVI. And this is beneficial when we start getting some of these events. And we'd like to look at it spatially to say, okay, well, look, this is Elk Fork, this is the Middle Fork, this is Long Branch. This should have a lot more of the flow coming down through there. So when we start looking at, Elk Fork at Madison or Long Branch or Middle Fork at Paris and Middle Fork at Holiday, we should be expecting to see a bit more of the flow coming down through this area than we would say the North Fork coming down through here. So this would be the North Fork at Haggard's Grove. So we would expect probably far less of an inflow coming into this point proportionate to what's happening here. This gives us a good frame of reference when we're looking at the data. As a water manager, I question all data. Doesn't matter any data. I question precip data comes into me. I question the stream gauge data comes into me. Everything is questionable. So I'm always comparing and contrasting data to each other to see what is the most reliable data. So that's just, I think, the nature of being a water manager. Always be skeptical of everything that's given to you. So that's just the viewing of the precip. So now we have to start going through and validating things. Let's start looking and start editing some of this data. So one thing we do is look at the North Fork at Haggard's Grove. What we notice is that they're here on the 2nd, it flatlines. Anybody that's a water manager, unless the gauge is frozen or you are in such a low flow scenario, seeing a gauge that's just flatlined is suspect, especially during an event where you have rainfall. So this is probably questionable data and needs to be removed. And so this would be the first thing that I'm going to start to validate when I go to the data validation part of it. And so we go from the visualization tab, and now we're going to go to the acquisition tab. This is where we're going to start to look at and edit data in here. So we could also visualize data from here as well. If we wanted to, we could also plot the data the same way from here from these time series icons. So it's kind of a choice on where you want to set up your workflow. But this is where you could access each of those data sets and start editing those data sets and validating those data sets. There's also data validation list and ways to validate these. Check with your local office to find out whether the water managers actually do the data validation. There are offices where there's a particular person or teams of individuals that are tasked to do the data validation part of it. So there might be a system administrator or data validation administrator that's going to validate that data for you, and water managers are just kind of the users of that edited data. In St. Louis, the water managers do the data validation. So they are regulating the projects and validating data. They do all of this. So this is the way it's set up in St. Louis. Not recommending that should be done in every district, but just check with your local district and your policies you have in your water management office. Anyway, that said, we go to Haggard's Grove and we pull up the data validation list for that location. And so in St. Louis, the way it's set up is if we have elevation record, we edit, all of the dependent data downstream of that will be recomputed. So from elevation, we'll recompute stage data, we'll recompute flow data, and in some instances, this is just a stream gauge, but if we were on the reservoir, it would recompute the storage the storage values based upon the elevation data, and it'll recompute the area, like the surface area. And then any other subsequent things that might come from that. So if there are some gate curves that might be used at some of the projects, so it might recompute the outflow from it. So all of that is keyed off of in St. Louis based upon the elevation data. So we always edit the elevation data to key off of what needs to happen for the rest of the data set. So we don't have to edit every single individual data set. That's the great part. And so that's all set up in CCP within our SWMS database. And so that's something to look into your office to see how that's set up for yours. If you don't have those set up, reach out to us and we can help you guide you into documentation on how to set those up. That said, we're going to remove this for this data set. We don't want to keep this in here. This is the erroneous data. So at the minimum, we will delete that data. That way we're not using that for calibration data or displaying it to the public site. We want to remove that so that it is no longer being viewed by anybody or used by anybody and thinking that it's valid data. Something you could do is maybe there was somebody out in the field that got a high watermark, or maybe the gauge tech was out there looking at the gauge at the time and gave us some information. And so for just examples here, we can, after we remove that data, we can also say, hey, we got a high watermark that's 702.2 or 3 or whatever. I mean, this is the high watermark here, and we're going to put that data point in there. And maybe it's just a singular data point we're going to put in there. Or maybe we have enough information to say that this is the high watermark, it happened at this time, and we're going to linearly interpolate from the last known good value to that point and then back down. Now this doesn't look like a typical hydrograph, and so this likely may not be acceptable. And I'll be honest with you, this is probably something that we wouldn't even do in St. Louis. This is just an example of something that can be done, especially if you're talking about like a significant event. You really need a high water crest event, like it's very much a piece of information. That is something we have done in St. Louis where we'll put at least the data point that's known. We may not interpolate between the two, but we'll put that data point in there as a reference. Filling in those during an event like this, during the middle of the hydrograph that's rising and falling, probably not likely, but this gives you an idea of what you can do. I will say in St. Louis, if it's on the recession limb, say we're over here on the 7th and 8th and we lost 24 hours of data, we would linearly fill that data. So generally, like the rule of thumb is somewhere around 24 hours or less, we will linearly interpolate as long as there's nothing going on in that time frame. So obviously in this time frame, there's something going on, so we probably wouldn't fill this in, but this is just an example. And so once we get that filled out, we can start to go to our modeling. So if you have any questions about our software, need some help, or looking for additional training, check out these links and look at the descriptions below. Thanks for your time.